Imagine a spacecraft or aircraft so advanced that its outer surface isn't just metal, it's alive with plasma. A soft, shimmering aura of charged particles wrapping around the hull, glowing faintly as it cuts through the air or void of space. This isn't science fiction. It's a real direction scientists and engineers are exploring today, a frontier in aerospace materials known as plasma skin hulls. Plasma skin hulls represent a leap beyond conventional engineering. Instead of relying solely on solid, static materials for protection and aerodynamics, they use an active layer of ionized gas, plasma, to dynamically shield and optimize the vehicle in flight. Think of it as a controllable energy field that flows over the surface, adjusting in real time to temperature, pressure, drag, or even radiation. The hull becomes adaptive, not just protective. It senses, reacts, and evolves. To understand how plasma skin technology works, we need to understand what plasma is. Plasma is often called the fourth state of matter. It's what happens when gases are energized so much that their atoms break apart into ions and free electrons. This process creates a highly conductive, electrically charged medium, something between gas and energy. Plasma naturally exists in lightning, stars, and the ionosphere of Earth. What makes it fascinating is how it interacts with electromagnetic fields and high-energy particles. Scientists realized that if they could generate and control plasma around a vehicle, they could create a new kind of interface between machine and environment. The concept of a plasma skin first emerged from studies in plasma stealth and hypersonic re-entry protection. When spacecraft re-enter Earth's atmosphere, friction from the air generates enormous heat, enough to burn through metal. Engineers discovered that a plasma layer naturally forms around re-entering capsules. Instead of fighting it, what if they could control it? That led to the idea of intentionally generating a plasma sheath to protect, stabilize, or even enhance performance. In modern research, a plasma skin hull is envisioned as a hybrid of solid materials and electromagnetic control systems. Beneath the outer surface, layers of conductive mesh, sensors, and energy channels generate and sustain the plasma field. When activated, high-voltage systems ionize the air or other surrounding medium, creating a controllable plasma envelope. This skin can then be shaped and modulated, forming an active barrier that responds dynamically to conditions. One of the most promising benefits is thermal protection. A plasma skin hull could absorb and deflect extreme heat by creating a buffer zone between the craft and its environment. Instead of relying on ablative materials that burn away on re-entry, plasma could continuously radiate and dissipate heat, allowing for reusable spacecraft and hypersonic jets. A plane traveling at Mach 10 could generate plasma layers that reduce surface heating dramatically, essentially creating a cool bubble in the middle of extreme temperatures. Another potential advantage lies in aerodynamic control. Plasma can alter the airflow around a body by changing its electrical and thermal properties. For instance, if a plasma field is formed along the leading edges of a wing, it can smooth turbulent airflows or reduce shock waves. This could enable quieter, more efficient, and faster flight. Imagine being able to reshape the airflow in real time, optimizing lift, drag, and stability, all through energy manipulation rather than mechanical flaps or control surfaces. The implications for stealth technology are equally profound. Plasma has unique electromagnetic properties that can absorb or scatter radar waves, making vehicles nearly invisible to detection systems. A plasma skin hull could act as a cloak, not by physically hiding an object, but by bending or absorbing the signals used to see it. Military research programs, especially in Russia, the US, and China, have already experimented with plasma stealth prototypes. While the full potential remains classified, it's clear that a plasma skin offers both defensive and offensive capabilities, reducing radar signatures and protecting against directed energy weapons. The concept also extends to radiation shielding in space. Astronauts traveling beyond Earth's magnetic field face constant exposure to cosmic rays and solar radiation. A plasma shield around a spacecraft could deflect or absorb harmful radiation, creating an artificial magnetosphere. In essence, humanity could bring its own version of Earth's protective field wherever it travels. This could make long-duration missions to Mars or deep space far safer. But plasma skin hulls aren't limited to protection and stealth. They could transform communication and propulsion as well. Current spacecraft often lose communication during atmospheric re-entry because the natural plasma sheath blocks radio signals. A controlled plasma skin, however, could be tuned to remain transparent to specific frequencies. By modulating plasma density and composition, it might even enhance signal transmission, turning the vehicle itself into a massive communication antenna. When it comes to propulsion, integrating plasma skins with ion or magnetohydrodynamic systems could create smoother energy transfer between the engine and surrounding air. For example, a hypersonic craft could use plasma to reduce drag while also channeling air molecules directly into an engine for combustion or plasma acceleration. This hybrid design could push performance boundaries far beyond what is possible with current jet or rocket technology. The physics behind it is complex but elegant. Plasma interacts with electromagnetic fields through what's known as the Lorentz force. This means the plasma layer can be shaped, accelerated, or contained by adjusting magnetic and electric field lines. It's similar to how magnetic confinement keeps plasma stable in fusion reactors. By embedding miniature field generators along the hull, engineers could sculpt the plasma's behavior like artists shaping clay, with precision and control. However, creating a stable, energy-efficient plasma layer in a constantly changing atmosphere is incredibly challenging. Plasma requires continuous energy input to remain ionized, and the power demands increase exponentially with surface area and density. Maintaining stability against turbulence, variable air pressure, and temperature gradients adds even more complexity. One of the biggest technical hurdles is finding materials that can handle the electromagnetic stresses without degrading or overheating. That's where modern materials science enters the picture. Researchers are experimenting with advanced composites and metamaterials, engineered substances with properties not found in nature. These can include self-healing ceramic layers, graphene-based conductors, and heat-resistant nanocoatings. The goal is to create a hull that's lightweight, durable, and electrically active. Such materials could both generate and withstand plasma fields without melting or cracking under stress. Another promising approach involves plasma skin generators, miniaturized plasma actuators integrated into the surface of aircraft. These devices create small jets of ionized air using electric discharges, influencing airflow directly. They're already being tested in drones and wind tunnels, showing measurable improvements in control and efficiency. Scaling that concept up to a full plasma skin hull would turn the entire surface into a single, continuous actuator. The energy systems powering these hulls could draw from multiple sources: superconducting circuits, compact fusion cells, or even wireless energy transmission. Future vehicles might receive power beams from ground stations or orbital satellites, maintaining their plasma layers indefinitely. Combined with AI-driven feedback systems, the hull could sense environmental changes, like turbulence or incoming projectiles, and instantly adjust its plasma field for maximum protection or stealth. Now imagine how this technology could redefine vehicle design itself. Without the need for bulky armor or mechanical flaps, aircraft could become sleeker, lighter, and more organic in shape. Spacecraft could have smooth, seamless exteriors that glow faintly when active. Plasma layers could even serve as visual indicators, shifting color or intensity based on system status. A deep red hue might signify defensive shielding, while a blue shimmer indicates aerodynamic optimization. The craft would be a living fusion of material and energy, responding dynamically to its surroundings. Beyond military and aerospace applications, plasma skin technology could influence everything from architecture to energy systems. Buildings could use plasma fields for lightning protection or atmospheric purification. Vehicles on Earth could employ plasma drag reduction to increase fuel efficiency. Even renewable energy could benefit. Plasma-based wind deflectors could enhance turbine performance, or plasma barriers could contain fusion reactions for power generation. Still, this vision comes with ethical and environmental considerations. Generating plasma at large scales involves high voltages and electromagnetic emissions that could affect communication networks or wildlife. The materials used to contain such systems might pose new recycling challenges. And like all dual-use technologies, plasma skins could be weaponized, used not only for defense, but for electromagnetic warfare or radiation control. As humanity advances, balancing innovation with responsibility will be crucial. The long-term potential, however, remains staggering. A fully realized plasma skin hull could be self-repairing, energy-generating, and adaptive to nearly any environment. On Mars, it could insulate colonies from dust storms and radiation. On Earth, it could enable ultra-fast travel with near-zero emissions. In orbit, it could create the foundation for truly resilient spacecraft, ones that don't just survive the extremes of space but thrive in them. Picture a future interplanetary vessel gliding silently through the void. Its hull glows faintly, surrounded by a living membrane of plasma that shimmers like liquid light. Micrometeoroids vaporize harmlessly upon contact. Cosmic rays bend and fade against the charged field. Inside, the ship remains cool, calm, and silent. It's not armor in the traditional sense, it's evolution. Technology that mimics the dynamic adaptability of nature, using fields and energy instead of brute strength. That's the true beauty of plasma skin technology. It represents a shift from passive engineering to active systems, from building walls to shaping environments. In essence, it's humanity learning to sculpt energy as easily as it once shaped metal. And as our world pushes deeper into the realms of hypersonic travel, off-world exploration, and energy innovation, plasma skin hulls might become the defining feature of a new era, the era where machines breathe, react, and defend themselves with the same grace as living organisms. The question isn't whether plasma skin hulls will exist, it's when they'll become mainstream. Every major advance in human mobility began as a dream: the wheel, the engine, the rocket. Plasma skin hulls could be the next step, a fusion of physics, materials, and imagination that transforms how we travel, explore, and protect ourselves in the universe. In the end, plasma skin hulls aren't just about speed or protection. They're about adaptability, the ability to evolve as environments change, to harness the same forces that shape stars and storms. They blur the line between machine and organism, between technology and energy. And as humanity ventures into the next century, that's exactly the kind of innovation we'll need. Technology that doesn't just survive the future, but becomes part of it. Hey everyone! If you enjoyed this video, make sure to hit that like button, drop a comment to share your thoughts, and subscribe so you don't miss any of our future uploads. Your support helps this channel grow. Thank you for watching.